Hello there and welcome back. Today we're going to continue our exploration of multivariate optimization and introduce a method known as the method of Lagrange multipliers. What makes this method a little bit different from, for example, the method of gradient or the numerical method of gradient descent is that the gradient descent and gradient methods don't allow us to impose constraints to our optimization problem, or at least not directly. So what the method of Lagrange multipliers does is it allows us to find the maximum or minimum of f, and it also allows us to introduce one or possibly even more constraints into our problem, which then allows us to have a analytical method to solve, for example, nonlinear optimization problems similar to that of what we did with linear programming. So as usual, what we're trying to find is some, say, solution in some vector space Rn, where we have, for example, n variables that we're sort of optimizing over, and we have some objective functions, say f, and we're trying to find that value x star such that f of x star is the maximum or even the minimum value of f. The method of Lagrange multipliers will allow us to find both the maximum and the minimum values of f subject to some constraints. And usually we're going to be representing these as g, or if we have more than one constraint, say g1, g2, down to say gk or something like that. Right, so let's just begin to state out the formal representation of Lagrange multipliers and talk about how it sort of goes about. So the structure of Lagrange multipliers goes as such. So we seek to optimize some function f of x, and again here x belongs to some vector space Rm, subject to the constraints, say g of x is equal to k, and here again x is an element of Rn, and here k is an element of the scalar field, say r. So g of x is equal to some number. This should seem very familiar to you, for example, from linear programming, because remember, we're seeking to optimize some functional f of x, which is equal to ctx, subject to a set of constraints, ax is equal to b. If this is just one equation, then b would be our number, and that would be our constraint. And if we have more than one constraint, technically g would now be a matrix, right? So that's pretty much the setup of what Lagrange multipliers requires, and it has one analytical requirement. So let's state that out. So requirement. It requires that the gradient of our constraint function g not be equal to the zero vector. Keep in mind that's not a number, that is the zero vector of Rn on the surface g of x is equal to k. Right? And you might be thinking, well, what exactly is g of x is equal to k? That is a level curve. For example, if you sort of, learned about contour curves with us, then g of x is equal to k is a particular contour curve because we want to know where g of x is equal to a particular number, and that number can range from, say, minus infinity to infinity. And where that plane sort of crosses that will generate that contour plot for us. So how does the method of Lagrange multipliers go in terms of finding the maximums and also minimums of our curve? So, step one. So the first thing that we need to do is find all values x, keep in mind x is a vector, and also lambda is going to be a number, such that the following things hold. The gradient of f at x is equal to lambda gradient of g of x. So keep in mind, gradient is a vector, that's a number. So if you sort of think about this geometrically, the gradient of g is just a scalar multiple of the gradient of f. So in some sense, these vectors are parallel to each other, and g of x is equal to k, right? So the same exact value x must satisfy both of these equations, so that of course is going to generate a system of equations that we have to solve. Typically, it's going to be a system of nonlinear equations. So if you have some numerical methods such as a multivariate Newton-Raphson method, that'll definitely come in handy here. Right? So once we find all the values x, we can, for example, call these x values, say, xb. These are going to be sort of like our basic solutions back in the linear programming world. So once we have all of our values x that make that true, and keep in mind, again, x is a vector, then what we're going to do is we're going to find the maximum value of f of xb, And that actually is going to generate the maximum value of f, subject to those constraints. And you're also going to find the minimum value of f when you plug in all of those xb's, and that's actually going to produce the minimum value that f attains. And those values xb that produce those maximum values are actually the optimal solutions x that we, seek out. Now, of course, I'm not going to go ahead and prove these things to you since this is more of an applied audience. If you're interested in the proof, definitely check that out, for example, in a Calculus 3 setting, which we'll definitely do in the future if we have not already. All right, so that's pretty much the setup and the algorithm for the method of Lagrange multipliers. Let's just go ahead and get into a couple examples to sort of illustrate how it's done. So let's assume we're interested in optimizing the two-dimensional input functional f of xy is equal to 3x plus y, subject to the nonlinear constraint x squared plus y squared is equal to 10, which of course outlines the circumference or perimeter of a circle. So the first thing that we need to do, remember what the goal of Lagrange multiplier is we first need to find all the values x that satisfy the gradient of f of x is equal to lambda times the gradient of g of x, and that g of x is equal to k. So we need to find all values x, in particular in this example we need to find all values x, y, and lambda that satisfy both of those equations, and then we're going to plug them into our objective function and then find our maximum and minimum values and where they are generated from. So since we need to find some gradients here, a couple first things that we need to do is we first need to define what our gx is. So this is our only constraint, and that is our variable part, and that's set equal to a constant. So we have, at least in our setup, that f of xy is going to be equal to our objective function. G of xy is going to be equal to that x squared plus y squared term, and our k is going to be equal to that 10. Now we need to find the gradient of f, the gradient of g, which are both going to be equal to vectors, and then that's going to construct a systems of equations in addition to that appendation of that particular constraint. So let's go ahead and find those gradients here. So the partial derivative with respect to x of f is going to be equal to 3, and the partial derivative of g with respect to, or actually let's do y. So the partial derivative of x with respect to y, that's going to be equal to 1. So from these two, that gives us what? So that means the gradient of fxy is going to be equal to, keep in mind, that's going to be fxxy times the unit vector in the first direction plus fyxy times the gradient, the unit vector in the second direction. So therefore, we have that the gradient of f at xy is just going to be equal to 3 times 1, 0 plus 1 times 0, 1, which is just going to be equal to the vector 3, 1. So what do we have here? So from our g, we can also find the partial derivatives with respect to x and y. So let's just go ahead and do that. So the partial derivative with respect to x of xy is going to be equal to just 2x. The partial derivative of g with respect to y of xy is just going to be equal to 2y. And then from these two, we can say that the gradient of gxy is going to be equal to 2x times 1, 0 plus 2y times 0, 1. And that's going to give us the vector 2x, 2y. Okay, so once we have that, now we can construct our system. So our system, remember, is going to be gradient of f is equal to lambda gradient g, and g is equal to k. So from that structure, that's going to give us the following equations. So the gradient of f came out to be 3, 1. And then we have lambda times the gradient of g. So it's going to be 2x times 2y. And then we have, in addition, that other equation, which was going to be x squared plus y squared is equal to 10. So let's just write that out in a more sensible manner. In particular, write that matrix equation as a systems of equations. So that means we seek to solve, how are we going to write this? 3 is equal to 2x lambda, 1 is equal to 2y lambda, and then x squared plus y squared is equal to 10. So we have 3 equations, 3 unknowns. Let's solve for x, y, and lambda. All right, so we can easily solve equation 1 for x. We can easily solve equation 2 for y. And then we're going to be solving them, or substituting them into equation 3, and then we should only have an equation with lambda in it. We can find our lambdas and then substitute those lambdas back here to get our x and our y respectively. So let's just go ahead and do that. So from the first equation we have that x is going to be equal to 3 divided by 2 times lambda. From the second equation we have that y is going to be equal to 1 over 2 times lambda. So substituting them into equation 3, that's going to give us 3 divided by 2 lambda the quantity squared plus 1 divided by 2 lambda the quantity squared, and that's all going to be equal to 10. So once we square those out, we're going to have 9 divided by 4 lambda squared plus 1 divided by 4 lambda squared is all going to be equal to 10. We can multiply both sides by 4 lambda squared, and that's going to give us 9 plus 1 is equal to 10 4 lambda squared. That's going to be equal to 10 on the left, and we can divide both sides by 10, and they cancel. And that's going to give us 1 is equal to 4 lambda squared, giving us that lambda squared is equal to 1 divided by 4. And then we can take the square root of both of the sides, and we have that lambda is equal to plus or minus 1 over 2. So these numbers that we found here, so let's just bring them over here. So lambda is equal to 1/2, and lambda is equal to negative 1/2. These are referred to as the Lagrange multipliers. Right, those are the Lagrange multipliers. Those help us find the location of the optimal values of f. All right, so now that we have our lambda values, now we can find our x and the y for which they're located. So remember, x was equal to 3 divided by 2 lambda. So once we substitute those in, we're going to have that x is equal to 3 divided by 2 times 1/2, or 2 times plus or minus 1/2, which is going to be plus or minus 1. So that's going to give us plus or minus 3. So x equals 3, or x is equal to negative 3. And then we can also find the values of y, because remember, y was equal to 1 over 2 lambda. So plugging in plus or minus 1/2, you're going to have y is equal to 1, and y is equal to negative 1. And those are paired up how I've written them. All right, so once you have those, that gives you our extreme points. So our extreme points are given by 3, 1, and minus 3, minus 1. And now I'm going to plug these into our function. So for example, f of 3, 1, and f of minus 3, minus 1. So f of 3, 1 is going to be equal to 3 times 3 plus 1, which comes out to 10. And that's going to come out to 3 times minus 3 plus minus 1, which is going to be equal to minus 10. So in conclusion, how can we interpret these results? So that means the maximum of f is 10, and it's located at the point 3, 1. And the minimum value of f will be negative 10, and that solution is generated from the point minus 3, minus 1. And that's how you do Lagrange multipliers. Let's go through another example just to make sure we got it. Now let's look at the example where the function we seek to optimize is not a linear function, because notice that we have a product of variables x, y. Usually when you have this, the algebra associated to the system you're dealing with is typically going to be a little bit more tedious, but sometimes still not impossible, right? And let's assume that we want to maximize subject to the constraint of x squared plus 2y squared is equal to 4, which you may know to be the shape of an ellipse. So we're going to start the same way as before. We need to find the gradients of f and the gradients of g, and then form our systems of equations. So the partial derivative with respect to x of xy, that's going to be coming out to y. And the partial derivative with respect to y of xy, that's just going to come out to x. The partial derivative of g with respect to xy, and the partial derivative of g with respect to y of xy. Keep in mind, this function is set equal to a constant, so that's our k and that's our g. That's going to come out to what? So that's going to be at 2x. And the partial derivative with respect to y, that's just going to be equal to 4y. So from these sets of equations, then we have the gradient f equals lambda gradient g equation that yx is equal to lambda 2x 4y. All right, so once we have that, then we can build our systems of equations as usual. So our goal is to solve y is equal to 2x lambda, that's the first equation that we have, and then x is equal to 4y lambda, that's the second equation that we have, and then we have our constraint equation, which is x squared plus 2y squared is equal to 4. So just as before, 3 equations, 3 unknowns, of course slightly more complicated, but that's okay. So let's see if we can go through this. Maybe you want to pause the video and try this on your own, but if not, let's just get right into it. So I'm going to actually approach this the same way I did it before. I'm going to solve for x in the first equation, solve y in the second equation, substitute, and sort of see what I get. So once I solve for x in the first equation, I'm going to have that x is equal to y divided by 2 lambda, and then I'm going to have y is equal to x divided by 4 lambda. And what I'm going to do here is I'm actually going to square these things. So square that, square that, square that, square that, and then substitute the squared values in the second equation. I think that's a little bit easier. So once we actually do that, we're going to have x squared is equal to y squared all over 4 lambda squared, and y squared is equal to x squared divided by 16 lambda squared. So substituting them in the last equation is going to give us what? So that's going to give us y squared all over 4 lambda squared plus 2 times x squared over 16 lambda squared is equal to 4. Let's see what we got going on here. So if we simplify this a little bit, so notice that that 2 and that 16 are going to reduce to a 1 over 8. So to get a common denominator, I'm going to have to multiply top and bottom of that fraction by 2. So once I have that, that's going to give us 2y squared all over 8 lambda squared plus x squared all over 8 lambda squared, and that's going to come out to 4. And then I'm going to multiply both sides by 8 lambda squared, just to eliminate that bottom, and that's going to give us 2y squared plus x squared is equal to 4 times 8, that's going to come out to 32, and then lambda squared. All right? Now, what can we do with this? Because we don't have lambda squared equals 10 or something like that. Notice that this right-hand side is precisely equal to the constraint that we have, and we know that that's precisely equal to 4. Isn't that nice? So we're going to have that 4 is equal to 32 lambda squared, which we can now solve for lambda, right? So once we have that lambda squared is equal to 4 divided by 32, which is going to be 1 over 8, and then we can take the square root of that if we desire, right? So we have lambda squared equals 1 over 8, and you can plus or minus 1 over 2 square root of 2 or whatever you want to do with that, but I'm actually going to leave it in that form, okay? So once I have that lambda value, now I can plug that in into my equations that actually formed here, right? Because notice that these equations that have formed have everything in terms of lambda squared, and lambda squared is equal to 1 over 8. So if I substitute them, what will I get? So I have x squared is equal to, remember, y squared divided by 4 lambda squared, right? So that's going to come out to what? So y squared divided by 4 times 1 over 8. 4 times 1 over 8 is 1 over 2, and that reciprocates to 2y squared. So I have this beautiful identity, x squared is equal to 2y squared. Now let's go back to our constraint equation, because this is actually going to help us out a very lot. Because remember, we already have our Lagrange multipliers. Remember, our Lagrange multipliers are the solutions of this very simple quadratic equation, lambda squared is equal to 1 over 8, so plus or minus 1 over the square root of 8. So now we just need to figure out the values of x and y that make that true, right? So remember that x squared plus 2y squared is equal to 4, and we know that x squared and 2y squared are equal to each other. So substituting them there for example, 2y squared, or substituting them for x squared will give you 2 sets of values, right? So that's going to give us what? So x squared is 2y squared, so we're going to have 2y squared plus that 2y squared is going to be equal to 4. So 4y squared is equal to 4, which means y squared is equal to 1, which means y is equal to plus or minus 1. And then I'm going to substitute in the other direction, because we know that 2y squared is the same as x squared. So x squared plus x squared is 4. 2x squared is equal to 4. X squared is equal to 2. So x is equal to plus or minus the square root of 2. Okay? So what do we got here? So those are our critical points. And we can also think about this from the contour plot perspective if we desire, because we should know how to construct contour plots by now. So if you construct contour plots, you should see that the point 0, 0, or somewhere near there is going to actually be a saddle point, and you're going to have a local maximum located over in these regimes. If you, for example, look at a closed bounded domain, and you're going to actually have a local minimum over here. Again, if you consider this on a a closed bounded domain. So remember that our constraint was an ellipse, in particular that ellipse, right? So what these points are, if you actually look at this graphically, so we have this point here, and that point there, that point there, and that point there. Because what is that point? So that point is going to be negative square root of 2, 1. This point there, that's going to be negative square root of 2 minus 1. That point there is going to be equal to square root of 2, 1. And that point there is going to be equal to square root of 2 minus 1. So when you plug those points in, what will you get? You're going to get exactly those type of results, right? So you're going to have some values that may give you equal values in terms of the maximum. And in particular, you're going to have a maximum value there and a maximum value there. And then you're going to have a minimum value located there and located there. But that's how you can use Lagrange multipliers to find the maximum and minimum values, which may not be unique, with respect to either one or more constraints. Hope you enjoyed, and I'll see you in the next video. Take care.